It's time for our second keynote speech. So I have the great pleasure to introduce Theo Skins, who's an associate professor at KU Leuven in Belgium. He will talk about, as you see, decision-focused learning. And a few highlights of his career is that I should point out that you have a consolidator ground of the European Research Council. So that's for the non-Europeans here. That's for his career bracket. That's the most prestigious thing you can get here in Europe. So, and I guess we're seeing here some of the outcomes. And then also had a best demo award at CPAIOR with his Sudoku app, which he demoed to me yesterday. So yeah. All right, so Tias, we look forward to learning everything about decision-focused learning. The floor is yours.
All right, thank you very much. Thank you also very much for the invitation. So the timing was quite right because we wrote a survey paper on decision-focused learning with Fernando Fiorete, people at my lab and as his lab, and it got accepted into chair. It's not online yet, but almost. So I thought this would be a great occasion to share a bit what we're doing there. But I want to talk about decision-focused learning and predictive optimization problems in the general sense. So let me start by taking the biggest possible step back that I could. And this is CPAIOR. So if you look at the research field of AI, which is rapidly changing, but still there are two big families of techniques within AI. One is everything that has to do with learning and predictions. And so it's focused on finding patterns and analyzing data. And with respect to the famous book from Daniel Kahneman, Thinking Fast and Slow, this is sometimes referred to as system one thinking that we humans also have. So that means instinctive thinking, reflexes, so immediately answering something based on the input that you get. And for example, given an image, is this a traffic light? Something that, well, not this image because of the resolution, but it's something that we can answer instantaneously. The other big family of techniques within AI are reasoning techniques, which has a focus more on knowledge, on expressing knowledge, on reasoning with that knowledge, logical inference, planning, search, and support. And so within this system one, system two, it's typically called system two. So it's slow thinking, it's more deliberate, multi-step, and logical. And it's not so much about recognizing something, but how are you going to act upon it, not just now, but also looking forward into the future. And so I think that one of the grand challenges that the field of AI is facing is that of combining reasoning techniques with machine learning techniques. And this is sometimes also called neurosymbolic AI. And I believe that with our technologies, and especially at the CPAIOR intersection, there's a lot that can be done here. And that's also where I position decision-focused learning. So the reasoning in this case will, of course, be combinatorial optimization. And this is this slow thinking, deliberate thinking, many examples of impactful problems that our technologies are able to solve. So in many cases, within combinatorial optimization, we actually use solvers and we follow a model plus solve paradigm, which means that we formulate our problem as an objective function and constraints over decision variables, and then we use existing CP or R solvers to find that. Now, when we talk about this neurosymbolic or combining reasoning with machine learning techniques, I think there's two big trends that we also see here at the conference. One is, for example, on using machine learning to learn how to solve faster. We get some nice talks on learning to branch, for example. And another is about using machine learning to learn part of the problem specification. So not so much to speed up the solver, but where the situation is such that you want to learn something about the problem specification. That's also what the focus of this talk will be about. I would say that within that, we can even split out a little bit further. So so where does the model specification come from, or how can we learn part of it? So one question is whether the structure is known or not. So in case some of the constraints are not known, and we had a nice poster by Louis Martin about that. There, the goal is to learn constraints, and this is sometimes called in the machine learning literature structural learning, or in the CP literature constraint acquisition, or in AI in general program synthesis, and so forth. But if the structure is known, so you know what kind of objective function structure there is, for example, or constraints, then the goal can be to learn the coefficients, to learn the prices, volumes, and so forth and so forth. And so that has many different names: predictive, optimized, infox learning, decision cognizant learning, and so forth and so forth. And so that we will talk about this. I will give you an overview of work in this bottom category. So, but before we go there, let's revisit the model plus solve paradigm a bit. So this model, this objective function and these constraints, where does it actually come from? Or what is in there? And in many cases, part of that is data. And so your objective function values can, for example, be expected electricity prices or travel time and so forth, right? But the way our solvers work is that they assume that these data are facts, that there are knowns and they do not change. But in practice, in many cases, for example, if we're talking about expected energy prices, it's an expected price, right? So it's actually something that's been predicted, that's been estimated in some way, and is then fed as a deterministic fact into the solver. And this can be in the objective, but also in the constraints, have volumes, durations of a job, and so forth and so forth. And so if we embrace this, and if we also look at how these estimations are actually happened, then in case these estimations are done with machine learning, we talk about predict plus optimize problems. So these are problems where you're going to predict part of your parameters, assuming that you have some correlated data. Because if you do these estimations naively, then maybe you're just going to estimate the expected energy price without taking into account in what kind of season you are, or your travel times without taking into account whether it's going to be a holiday or not. So if you have this kind of correlated data, if you know some properties about what you're going to predict, then in many cases, we use machine learning typically to make more accurate predictions. So we use a machine learning model, and then those predictions make up part of the problem specification. Okay, so from a neurosymbolic kind of perspective, or from an optimization perspective, well, I think the way I like to think about it when we look at a problem and we determine what should we use where, is that whenever part of the problem has some knowledge that is easy to formalize, easy to make explicit, for example, the number of vehicles or their capacities, then I believe that should be part of a constraint specification, something where we use exact reasoning techniques for. But if some part of the problem is actually hard to formalize, it's more implicit knowledge, for example, preferences, for example, expected consumption, expected use, and so forth, then it might actually be better to use machine learning techniques for that. All right, so these type of problems in general, that's what we call predict plus optimize problems. So that's the optimization view. Now, from a machine learning view, standard machine learning only considers this first part. And so you have a data set, you have some correlated historic data, and then you build a machine learning model to make predictions. So in standard machine learning, we typically assume that there's plenty of data that is also easy to evaluate. There's standard metrics in case of classification and regression problems, and there are many well-known loss functions available that you can use. Now let's add the optimization part to it. And what now changes is that we're actually doing machine learning at the service of our optimization solver, right? In machine learning, the goal is no longer to just get predictions. I mean, what do we do with the predictions? Well, therefore, a downstream optimization task. And that means that to even evaluate the quality of your predictions, you will have to call the solver, right? And that also raises the question, okay, so what kind of loss function should we then use? If we're not evaluating with standard ML measures, then should we really use the standard ML loss functions? And so this is typically multi-output classification because you have multiple parameters for which you solve a single optimization problem. And in many cases, the amount of data available is also fewer. So that's a challenge. Okay, so that's a bit to set the scene of the talk. So we'll do a warm-up with some perception-based solving based on the visual Sudoku app. In that case, we're just going to pre-train the neural networks, but we're going to be smart about how we use the predictions. That can already get you pretty far. And then the main part of the talk will be about decision-focused learning. So how can we do end-to-end training with the solver in the loop? And then we'll close off with some open challenges in the bigger picture of the ERC project. Okay, so Pierre already mentioned it, and so indeed at AAAI, we won this nice award for the demo application of the Sudoku assistant. So the idea is that you take your phone, so it's available on the Google Play Store, so you can actually download it yourself. And then you have a newspaper Sudoku image, it will automatically try to recognize the box of the image. And so if you're solving on a Sudoku and you're stuck, you can take a picture and then it will analyze it and so forth. So my mother-in-law solves the Sudoku every day. She was my inspiration. Yeah. All right. So we can standard computer vision to recognize the rectangles. That's not the hard part. If we have that, we can cut this aligned image, the box that was recognized, into 81 pieces. This does introduce some noise. And then for each of the cells, we need to predict whether it contains the value 1, 2, up to 9, or whether the cell is empty. So this is slightly custom because it's not, you cannot use MNIST or SVHN type things because you also need to predict whether the cell is empty, but that's really like a tiny change, right? So you can use standard convolutional neural network techniques here. All right. So with that, you can get for every cell the predictions, and you can use that. Okay. So solving the Sudoku, of course, we will use constraint solvers here, right? That's one of the main examples, starting examples, pedagogical examples. In this case, we're using a Python-based library called CPMPy that we develop. It's solver independent, translates to many different kinds of paradigms and technologies. And it's convenient to integrate with machine learning representations. Okay, so we have our neural network. We then, for every cell, we take the prediction, the Argmax of these probabilities for each of the possible cell values, and then we can give that to the CP solver. So what happens? So if we use MNIST data, so very clean individual numbers, and we arrange them on a 81 by 81 grid, and we add some empty cells in between that. Then if we focus on the cell accuracy, so the accuracy of individual cells, and with this MNIST specifier gets about 99.5% accuracy, which is very, very high. But if you look at the amount of grids that it can solve, so the amount of actual Sudokus, it's only about 73%. So that 0.5%, and remember there's 81 predictions per grid, right? Actually, it's quite hurtful. And in many cases, it's actually because the solver cannot even find a solution. There is some conflict in just, for example, 2 of the predictions. That means that no solution is found. If you look at the real data from the app, then we have to use a different architecture, but that's okay. So it's more noisy, so the cell accuracy is a bit lower, but the errors are more concentrated on specific grids, for example, due to lightning. But we still get not too wonderful. This wouldn't be a too impressive app with 77% accuracy. And again, in many cases, we don't actually find a solution. The solver simply says, no, this cannot be a Sudoku. So let's look a bit into that case. Instead of just going into fancy machine learning, let's just analyze the situation a bit. So why are there so many problems unsolved? So what we did was for each of the cell, we take this predicted value, so the argmax over the probability that it's a 1, that it's a 2, that it's a 3, or that it's empty. And you need all of those 81 predictions. And actually all 81 are then used together in the solver. And when it says that there is no solution, it just means that at least one of those interpretations is wrong. Okay, so if one of them is wrong, why don't we just use the next possible interpretation. Indeed, if we plot this discrete distribution, so for every cell, every color represents the probability that it is of a specific value. So here the probability is 5, probability is empty, probability is 2. And if you look at the very top, you see that there's 2 cells, and probabilities are pretty much everywhere. It's the border that's confusing the neural network. And so both of these cells at the top, their argmax value is a 5. But clearly, there are many other values with similar probability that could also be feasible. But if we just use a prediction, this is invisible to the constraint solver, right? So instead of doing that, instead of first doing the argmax and then taking all 81 argmaxes into the solver, let's do this inference jointly, okay? So we're going to treat the prediction as a joint inference problem for which we use a constraint solver. So we will, for every cell, we will use all 10 probabilities, and we still have our constraints, but for every cell in the matrix, we introduce a perception decision variable. So this one will choose what interpretation it gives to that cell. Is it a 1, a 2, a 3, a 4, and empty? And then the objective function is actually which interpretation it chooses multiplied by the log probability predicted by the neural network. So the argmax interpretation will still be the best one you can take, but if that one leads to an invalid Sudoku, then it can take another interpretation. Okay, and so we're going to find the maximum likelihood joint interpretation of the image. So in machine learning, this is known as a structured output prediction, and actually CP and mid solvers has been used in NLP before. In that case, it was for coreference resolution. And so to avoid cases like having 3 verbs in a row, that doesn't make any sense, but you can just take the next most likely interpretation. Here we do it with a much more constrained problem. So let's look at the results. So as you can see here on the right, so the number of unsolved cases, of course, drops to 0 because we're asking for an interpretation that is valid. So it will always give an interpretation that is valid. And we also see that in case of the MNIST data, we can now solve 99% of the instances correctly. And so just a few of the cells had to be corrected, and that leads to much more grids being able to solve. Also, in case of the real data, it makes a bit different. This is at the cell level, and this is at the grid level. We now solve 93%. And if we enforce that the interpretation is unique, we can solve up to 94% with this. So there's a number of other things that we do. For example, we make a difference between handwritten predictions and printed predictions that gives us an additional boost. So this is integrated into the app. All right. So this was an example where pre-training gave moderate results, but looking into what is going on and actually integrating the inference part, just the inference part, into the constraint solver already gives very good results. But for other problems, we might actually want to do the training with the downstream task in the loop. So let's have a look at that. So we will be talking mostly, and the survey also mostly talks about techniques that learn coefficients of the objective function. And for example, this energy price aware, you got a short intro by Senna just before lunch. So this is an energy price aware scheduling problem. For each of the time points of the coming 24 hours, so 24 predictions, for example, we have to predict what the hourly energy price will be for that hour. And then we need to solve a price-aware scheduling problem where we have a number of jobs that we can distribute over different machines so as to minimize the expected energy price. Okay, and so this is, again, a prediction plus optimization problem. We need to predict some of the parameters, and those will then feed into the objective function. There's many, many more examples. For example, in steel production to avoid waste, predicting steel defects, money transport, other waste collection, and so forth and so forth. So why is pre-training insufficient here, or when is it sometimes insufficient? So here on the bottom right, we see an extreme example. It's one of the most extreme examples that we've seen. But the green line is a mean square error. So that's the training error from a machine learning point of view as the training progresses. And the red line here is the regret. That's the error of the decision problem over the different efforts. And so what we see is that even though from the machine learning point of view, our predictions are getting more and more and more accurate, if we evaluate the downstream optimization problem, actually it's becoming worse and worse. So how can this happen? Well, this is actually because we're feeding all 24 predictions into the constraint solver. The constraint solver is again doing some kind of joint inference problem. So although we measure the error of each price prediction independently here, this one takes them together in groups of 24. So it's a joint inference, and so it's also a joint error. So it's not just an average of the individual predictions. So some of the errors are worse than some of the other errors. In the journal paper, we have this very clean pedagogical example to show it, the survey paper a bit more. So this is very simple, a 2-item knapsack problem, unit weights, capacity 1. And the true value is that item 1 to get a prediction of 2.5, a value of 2.5, and item 2 has a value of 3, right? So the blue point is the true prediction. And if you use that true prediction, then you will choose item 2, and that's the right decision here. But then we will use a predictive model. So the predictions for both item 1 and item 2 can be something else, right? And so if we focus on these green crosses here, then each of these has a different mean square error, right? So you get a different error either for item 1 or for item 2. So the mean square error for each of these points is different, but the regret, the impact on the decision is exactly the same. In all cases, you're still going to prefer item 2 over item 1. Right, so mean square error here is not correlated for these examples with regret. On the other hand, if we look at these 2 points, then their mean square error is the same, because there's an equal amount of under prediction for one item as there is an over prediction for the. No, that's not true. The item 1 actually has exactly the same value, and while item 2 should have this value, it's actually now given the value below. So the mean square error of those 2 points is the same, but the regret is different. So no, it should, that's what it is. It should have been this one, right? Yes, so it should be this plus with this plus. I'm sorry, I did wrong. So if you look at this plus and this plus, then they have the same mean square error, but the regret is different. All right. So again, showing that the two do not have to be correlated. All right, so now that we know that this can happen, can we actually find out which of the errors is worse? Can we, because you have, for example, cost-sensitive machine learning, things like that. If we can just find out which of the errors is worse, we can just penalize some of the errors, some of the types of errors to quantile prediction, whatever, and be done. And the answer is no, because we're giving this to a combinatorial solver. The way that the errors interact is combinatorial. So we need to actually call the solver to find out whether the prediction error is of such a kind that it changes the outcome, the outcome. So we can formulate this as a bi-level problem. I tried to make it more readable. I don't think I succeeded. But so the orange part is the predicted cost vector, so C hat, which uses the network parameters in purple and the features in blue. And based on that, we're going to compute what is the cost. If we know the cost up front, that's the right side after the minus, the top line. And that's what the true objective value would have been, the true energy price. And then if we use the predictions to find a solution, but we evaluate it with the true cost, how much worse is that? And that's the regret. And so if we want to optimize our network parameters directly, that would mean having to solve this kind of bi-level optimization problem. But there are some challenges. And so the F, the feasible space, is in this case implicit, and it's specified as constraints, and we don't assume that we can list all feasible solutions. Actually, calling the solver can be an NP-hard problem, and there could be non-uniqueness in the solutions. And then lastly, if you want to use gradient descent learning, the gradients of this are actually non-informative. Let's take a little bit a deeper look at this last point. So let's say that we have so let's say that the weights of our network are such that we predict a certain combination of values that leads to a kind of decision here. If we now slightly perturb the predictions, so slightly perturb the weights of the neural network, we get somewhat different predictions. Now, these predictions might actually not have any change on the outcome. Let's say that this is the most expensive time slot, the morning, everybody wakes up and wants a nice cup of tea, and so lots of kettles going on, high energy prices. So if this is the most expensive time slot, and we're going to overestimate the electricity price at this moment, it's not going to affect our decision. The scheduling will still avoid this specific time point. But if our error is such that we under-predict a specific time point, then at some point, and for different kind of weights of network, we're actually going to jump to a different solution. For example, this solution, where this time point now becomes very interesting, and so the scheduling puts lots of tasks there because it looks like it's cheaper or as cheap as others. So at that point, so nothing changes, and then bam, different solution. And so this kind of function doesn't give us meaningful gradients, so we cannot use it in gradient descent learning. Now imagine for a second that we could. So this is the typical pseudocode of standard gradient descent learning, where for each epoch, we have a training instance, sample training instance, we get the predictions from the neural network, we have some kind of loss function, and then we backpropagate over the loss function, and we update the weights of the network. All right. So if we would have a valid way to compute gradients for regret, then it would actually be only a very small change in the code. We would still get the predictions. We would then use those predictions to call our solver, get the regret, and then backpropagate over that. Okay, and actually the implementation on the machine learning side is very easy. And there's a number of nice libraries available that help with that. So this is a more pictorial representation from the survey that Senna also showed. And so the real challenge here is that we need to be able to compute the gradient of this. To compute how will the solution change if we make a change to the predictions in the predicted cost weight. And so within gradient descent learning, there's actually four, that's the categorization that we have in the survey paper. There are four different types of techniques that people have coming up with valid gradients for this problem, such that we can use gradient descent learning. And I'll talk a bit about each of the four. So they do have assumptions on the objective function, for example, convex or linear. Usually it's linear in the predicted parameters. Some also have assumptions about the constraints, about the decisions being continuous or mixed. And then between the blue and the less blue ones, this one makes an assumption on the kind of solver we will use, and these do not make such an assumption. So based on this table, your expertise or preference, you can also choose a bit what kind of methods you would want to look at. All right. So I'll go over each of the four categories and share some insights in how they work. So the first one is about getting analytical, doing analytical differentiation over the optimization mapping. And we'll start with the easiest type of problem. So assume that the decision variables are continuous, so that part is okay, and that it's an unconstrained optimization problem. Okay, so we want to find some value where we optimize some function with the predicted coefficients and the continuous decision variables. All right. So here, the mapping from, so given a cost, we will get the decision vector, right? So that part of the mapping is clear. Yeah? But given a certain decision, we don't know how that actually maps back into the coefficients. So the opposite side of that map is not available, and that's why we can actually not backpropagate, or we cannot differentiate over it either. However, the nice trick, and this was identified already in 2016 by Gould et al., is that we can actually define an implicit mapping. Namely, we can take the optimality condition. So the first order optimality condition says that the first order derivative of an optimal solution has to be 0. Okay? So now we have this implicit mapping. It's still not an explicit mapping from the coefficients to the solution, but it is a condition that needs to be held. And so you could actually do implicit differentiation of this optimality conditions. And under the assumption that your function is twice differentiable, this is a valid gradient for that unconstrained continuous problem. All right, so if f is twice differentiable, this is what the gradient would be. Okay, so what if it's continuous, but it is constrained? So linear programming, for example. In that case, we can actually add the constraints to the objective function, maybe add some Lagrangian multipliers and so forth. But instead of doing that, let's just use well-known optimality conditions that are used by MIP solvers, namely the KKT conditions of that linear programming problem. So these are also valid optimality conditions, and then you can do implicit differentiation over those. It's a bit more complex than this, but this is also a valid gradient that you obtain. All right. Okay. So that's for quadratic, and still your f needs to be twice differentiable. So that's for quadratic actually the function f, so not linear programming, quadratic programming. Function f needs to be quadratic. All right. So what if it's well, let's ignore this one for now. So what if it's continuous, but the objective function is linear? So it's constrained, but the objective function is linear. Then, because its objective is linear, the second derivative or this, has a value of 0. So then we divide by 0. Not a good idea. So one proposal, a nice proposal by Wilder et al. Was, let's actually do a regularization. Let's add a quadratic regularizer. And then if we add this, for example, the L2 norm over the decision variables with some scaling factor, then in this case, we get a quadratic objective function, and we can use the technique from the previous slide at the bottom. All right. So by adding this quadratic regularizer, it's a quadratic objective function, and we can do that. And there's actually an interpretation of why this now becomes a smooth mapping. So we write it in the survey page, so you can rewrite this into the following form, which shows that we're now mapping this specific point, the vector of cost coefficients divided by that scaling factor. We actually have a continuous mapping from that point to the feasible region. That is a problem that we're now solving. Another approach, which actually found like the inspiration came from interior point solving. So what interior point solvers do is they don't add a kind of regularizer like that, but they add the log barrier within their techniques, and so that corresponds to this. So also in this case, the second derivative exists. And so you can actually, again, do the implicit differentiation of the KKT conditions, or if we stay closer to what some interior point solvers do, we can also use the homogeneous self-dual. These are also optimality conditions. We can also implicitly differentiate over that, and then we also get valid gradients. All right, so what now if our decision variables are discrete? Okay, because we still assumed that these are LPs, that they're continuous. So if they're discrete, then one proposal, Wilder et al. Again, is to relax, to just ignore integrality, right? Why not? And you take the linear program, and then you can use any of the methods from the previous slide, right? Now, this, of course, will depend on the tightness of your linear relaxation versus the original integer formulation. That's why, for example, Faber et al., they proposed to actually tighten that relaxation. So by using cutting planes at the root of the MIP formulation, you first collect all of the cuts, and then you will get a tighter formulation, and then you can use again the techniques from the previous slide. Okay, so all these methods, so these methods now fall into the second line of that table. And so here we do analytical smoothing of the optimization mapping. And so the smoothing can be either with the quadratic one, which is not shown, or with the log barrier. And then you can also smooth the constraints in this way. Okay, so that's the first two rows of the table. I give you a bit of an overview. And there's many more works that we're talking about in the survey. Let's look at the third row then. It's really a very different kind of technique. So this one places no assumptions on the solver. So you don't need to use a primal dual solver. You will not need to use those dual values. It comes from, especially from the probabilistic programming community. And so here the idea is that we're going to smooth our solution, and hence also the gradient that we need to extract, by perturbing the predictions. So if we perturb the cost vector, so the cost vector C should be C hat, the predicted cost vector, we can actually perturb it by sampling from a well-chosen distribution. And so all of the effort, all of the magic of this type of work is in what kind of distribution that you're going to sample your noise from. But assuming that there is such a well-defined distribution, and there's multiple, and you can sample from that and add it to your cost and then optimize for that. So why is this a good idea? Well, this is actually a form of stochastic smoothing. And so if you do this multiple times, then what you get is you actually get a smooth estimate of that value of the solution and hence of the regret. And so imagine that you're here at this point. If you add some noise, and then you might end up in this, a bit more to the left. And if you add, and you do another iteration, you sample a different amount of noise, then you actually might end up at this location. Okay, so your predictions are still here, but by doing that, by doing these multiple samples, you get one here and one here. If you take the expected value, you average that value, then you get to this point, right? So by taking multiple samples, you might actually switch, your solution might switch, and so you automatically smooth the regret value that you obtain. And that means that it now becomes continuously differentiable. And so the details are clearly in the survey, but that's the idea of this random perturbation. So what's nice is that it's solver agnostic. So it doesn't make any assumption on how you get your X star. Okay? It just makes assumptions on the distribution and where you get your noise from. And what's also nice is that with this kind of work, you can actually use your combinatorial optimization problem anywhere in the neural network. So this also places no assumption on using regret as a downstream loss function. You can use Hamming loss, or you can actually add additional neural network layers on top. So if you want to do your optimization as a layer in between others, then this is the right kind of techniques to look at. And then the fourth row in the table is differentiation through the use of surrogate loss functions. And the most well-known, and also in experiments, one of the most empirically stable methods is the SPO plus loss from El Maktoub and Grigas, first on arXiv in 2017. So what they do is they have a very nice derivations where they show that regret itself is indeed not differentiable, but you can define this convex surrogate, which is an upper bound on regret. Okay, and now this convex surrogate actually has a very nice, very simple subgradient. Okay, that you can use in gradient-based learning. What you need to simply do is you take the true optimal solution, so that gives you a vector of the decision variables, and from that you subtract calling the solver with this little trick here, 2c hat minus c, which is actually the predicted cost factor C hat, but then perturbed by the error that you have. That's C hat minus C. So if you know the cost factor, it's actually doing a perturbation in the direction of the error. And then you can also see it maybe as a finite difference method. Then it takes the difference of that, and this is a valid subgradient. So let's say that you have a binary problem. Either for one of your decision variables, either their value does not change, so it's 1 here and it's 1 here, or it changes and it's 1 here and it's a 0 here. And then the subgradient tells you, okay, in your next iteration, you need to predict something higher, or it was a 0 here, and then after this change, it's a 1. So it means that you get a -1. So in your next iteration, you need to be lower or opposite. Okay, so that's the idea. So this works really well, but is specific to regret as a downstream loss function, and it assumes that the true cost factor C is available, which is a very fair assumption actually. So that's one kind of surrogate loss function. There's other surrogate loss function that have been identified. For example, there's a relation between optimization, which maximizes or minimizes an objective function, and an objective function actually inducing a ranking over the feasible space. Indeed, your objective function induces such a ranking. Now, ranking in itself is already well studied in machine learning, especially in information retrieval, where they have specific loss functions that can penalize between different rankers. And so with the true cost, you get a certain ranking. With your predicted cost, you might get a different ranking. And so if we, for example, assume that we have a finite subset of feasible solutions, I will only tell you in 3 slides how to get that. But if we assume for a second that we have a finite subset of relevant solutions in the feasible space, then we can actually get this empirical distribution that says that this should be the best one, and it should have the highest value and highest probability. And then these are the other ones. But if you use the predictions, that's actually how the values look like. And so under this finite set, we now have 2 rankings, and we can use existing loss functions from the learning to rank literature over that. And one example, for example, is the listwise loss function. And so if we assume a discrete exponential distribution over the solutions induced by the objective function with some scaling parameter, then these can be seen not just as the value of each of the feasible solutions, but this can be seen as a probability distribution over that finite set of samples. And then if we treat this as a probability distribution, find here, then we can use existing losses like the very well-known standard Kullback-Leibler divergence loss between 2 empirical distributions. Okay. So that's, again, a surrogate loss formulation, one that is consuming a lot of energy. And we can use that loss function instead. All right. So I haven't told you where that finite sample comes from. And so far, I've also only focused on defining a proper a loss function, or actually defining a gradient, a surrogate gradient that you can use in gradient descent-based learning. So defining that gradient is one big challenge in decision-focused learning. The second big challenge is that you're going to call your solver for every epoch and for every instance to be able to compute that loss function. And so a simple trick that you can do is to actually cache the feasible solutions that you obtain every time that you call your solver. So whenever you call your solver, you can keep the answer, you can store it somewhere, and then you can use your loss as before. And if you do that, then you automatically get a cache of feasible solutions that you can use, for example, in these learning to rank type of losses. All right, but there's other things you can do. For example, you can even skip the solver, because in gradient descent learning, we're only doing small weight updates in every iteration. So if you solve the problem for a certain weight, for a certain network weights at some point, you only make a small change. By definition, by trouble of this problem, your actual solution might not change. So sometimes you can actually just skip the solver and do that. We don't know when exactly you should or shouldn't skip. That's a bit of an open problem, but we did, for example, some experiments, and we're even calling the solver only 5% of the time. We do a lot of epochs, right? But 5% of the time, we actually get very good results. So also in the survey, there's an experimental study that contains a bit of that. All right. Okay, so indeed, as I just said, so the survey paper gives the survey. It also talks about non-gradient based method. It also talks about other related fields. But the second part of the survey paper is actually an experimental evaluation. So we have these benchmark instances that come from the existing papers in the survey. So it's a shortest path problem with the linear objective function, portfolio problem, Warcraft shortest path, energy customer scheduling, and so forth and so forth. Okay, so all of this is also available on the repository that contains the data and the code of all of this. So in the experimental evaluation, we evaluated the following methods. So of course, prediction, focused learning at the top, and then analytical smoothing, smoothing by perturbation, and surrogate losses. Now, one thing that's typically not discussed a lot is that you also need to tune your hyperparameters. So we're being very open about what kind of grid, based on our experience, we define this kind of grid, and then we do a standard machine learning hyperparameter search over it. And so, yeah, you can have a look at that, because some methods are actually pretty difficult to tune. For example, QPTL, the quadratic programming task loss, the multiplier of that quadratic regularization can be tricky to tune. So sometimes it gives strange results or less desirable results. And so some examples, the top one is the energy cost aware scheduling. Many methods perform fairly similarly. CPAIOR generally does well. Portfolio optimization, here it's quadratic constraints. So some of the probabilistic methods seem to behave differently. Warcraft shortest path, here we couldn't apply, even though it's a shortest path problem, we couldn't apply the analytical smoothing techniques because it was too slow, but the other ones work fine. Also, the error of the prediction focus is very high here. So there's a lot of uncertainty in that data, and the difference, the effect of using decision box learning is very big here. Diverse bipartite matching, also some results, okay? So in terms of runtime, we added at least one experiment. So here, the 4 on the right, they use that caching technique, which they only call the solver 5 or 10% of the time. Clearly, it has a very big influence. They're also not always the best in the previous experiment, but as you can see, in terms of runtime, this is more manageable and more scalable. Okay, time-wise, I guess now it's a good moment. I just added all of the open challenges in one slide. In the survey, we take a bit more time. We talk about each of these a bit more at these. But so I think one general category of open challenges is about improving the theoretical foundations. And so Senna had this poster on what if the constraints change. And so generalization is clearly in machine learning always an important aspect. And here we're talking about generalization with respect to changing the machine learning, but we should also be able to generalize with respect to the decision problem. I think more connections with bi-level optimization can be made. There's some nice works, especially with respect to SPO, on theoretical guarantees or convergent guarantees. Much more to be done there. Also robustness, risk sensitivity. I had some conversations before, some people here that are working on that, which is very nice. In terms of capabilities, and so what we presented, what the major focus of the survey and also in the literature is linear objective, linear in the prediction, in the sub-objectives, but also there's room for nonlinear objective functions, and certainly in the constraints, multi-stage problems, or real-world data and multimodal data, and so forth, and also scalability, or even zero-order gradient estimation methods are very promising. So for us in our research lab, how this fits in is that currently, and we have the model plus solve paradigm, we have this assumption that the user formulates a problem and that's it. but we're looking into using machine learning to learn these coefficients, for example, the prices, but also to learn preferences. And then ideally, what we hope is that that constraint solver can not just give a solution, but also explain the solution that it obtains. So that's explainable constraint solving. And then even better would be if we can make some stateful interactions where a user specifies a problem, asks, why is this the case? And can it be this way? Can it be this way? Can it be this way? Right? And so we have a little bit of that also in the Sudoku assistant. I guess that's why we might have won the award. And so we also provide we don't just solve the Sudoku after it's been analyzed, that would ruin all the fun. We also provide these stepwise explanations of what the easiest next step would be. Now we're looking into learning what kind of explanations are preferred by users, and so to also integrate machine learning on that side and so forth. So that's actually the topic of this ERC consolidator grant. So it's a 5-year, €2 million project, and I'm hiring postdocs. So if you're interested, let me know. Okay, so to close off, so key takeaway: prediction plus optimization within the neurosymbolic landscape. And I think the idea is that let's use our solvers, let's use our techniques when we can make explicit constraints easy to formulate, and let's use machine learning and learning on the parts that are hard to formalize. And then with respect to decision-focused learning, so I focus here especially on gradient-based methods, because then you can use neural networks as input. And we talked about 4 categories. All of the data and the code is available here. And there's also a ton of open challenges because it's a relatively new field. And that's what I wanted to share.